So we are going to be examining how do standing waves work in pipes. And we firstly, before we talk about that, we need to think of the classification of pipes, because there are two different types of pipes that we need to think about. One pipe is called an open pipe, and one pipe is called a closed pipe. So an open pipe basically means you've got a pipe that is open on both ends. So this end here is open. That means air can get in or out. And this side here is open. So think of it as if you've got, like, you know, a toilet roll, that middle part, you know, the holder of the toilet roll, that's an open pipe, right? Or any sort of thing that you can, that's open on both ends. So you can think of, for example, a water pipe that's cut open, that's open on both ends, right? Now, a closed pipe, on the other hand, is not open on both ends. It's closed on one end. So it's not a closed container, right? Air can get in and out. It's a pipe. So this side is open, but this side is closed. So they're not the same. They have different sort of situations, and you need to be very clear about this. So an open end is open on both ends. And a closed pipe is, or closed on one end. But importantly, it's open on the other end. Now, the key thing, of course, is that for an open pipe, air can get in and out on both ends, whereas for a closed pipe, it can't. And so if we examine open pipes, they'll be quite similar to strings in the sense that you've got this situation where, you know, you've got some sort of, while the waves are sort of bouncing about between these two sort of ends, there's going to be some sort of potential to get a standing wave. Now, for an open pipe, if we're talking about particle displacement, think of it as if you've got a crowd. It's kind of like a crowd, and you're kind of trying to push out. But if you're trying to push out, because you're here at the opening, this allows you to move the most, right? Whereas if you're stuck in the middle of the crowd, you can't move that much in comparison. Which means these sides are now antinodes. So for a string, the ends are nodes. For an open pipe, as far as your particle displacement is concerned, then these are antinodes. But I mean, while whether it's a node or an antinode is different, I mean, mathematically it doesn't change much, because while we might draw the diagram differently like this, you'll notice quite quickly, I think, if we call this length L, well, we'll still call this the fundamental mode of vibration, because the ends need to be an antinode, which is still also called the first harmonic. And if you continue and basically look at the sort of wavelength, you can notice that, you know, this wave will continue. And so basically this L is half wavelength. So you'll notice that for lambda 1, it's actually 2 times L. And for the same reason as before, we're using V equals F lambda, where F equals V over lambda. So this will be V over 2L. And you'll notice that this basically is exactly the same as what we had for strings. And it is. But you'll need to notice that, well, it's different this time in the sense that it's now antinodes on both ends. However, numerically, not much has changed. And of course, if we keep the pipe length the same, again, it's not the only wave we could have drawn. I do need an antinode at both ends, but I could also have an antinode in between. So I could kind of do this situation, right? Now, of course, that means I've got nodes. So here I had one node, right? I'm going to have two nodes. I'm going to have an antinode here as well. And so this here is the next level up. So this is going to be called the second harmonic. And that will have a lambda 2. And you can probably see that this lambda 2, if you follow this wavelength, will just equal L, which means this F2 must equal 2 times F1. Okay. And that's basically what it is. And things haven't gone away. It's still called the same thing. So this is still called your first overtone. And so you'll notice this very similar situation that's going on. And so So I guess if we count it, this will have 2 antinodes and 1 node. This is your fundamental mode of vibration. And that will give you a lambda 1 equals 2L and an F1 equals B over 2L. We'll notice that if we introduce the next one up, then you'll count 3 antinodes. You'll count 2 nodes. And this is called your second harmonic, which will have an associated lambda 2 of L, and it will have an associated F2 of 2F1. Then you've got the next one up. So we could add in, well, another one. So you'll notice here that we've got 1, 2, 3, 4 antinodes, which gives us 1, 2, 3 nodes. And this will be your third harmonic, which gives you a lambda 3. Now, you can probably see that your wavelength is just this part. So it's going to actually be, well, you're splitting it into 3 parts, so it's going to be 2/3 L, and your F3 is going to be 3 times F1. So if we have a pipe, and if we kind of have a split in between, but basically you can see that we're going to have some sort of idea of some sort of thing like this. Then we're going to have lots of nodes and antinodes. Specifically, if this is the nth harmonic, then you're going to have n plus 1 antinodes. You're going to have n nodes. And your Fn, I mean, if you have n plus 1 antinodes, you're going to split it into n equal parts, and your wavelength will be 2 of them, so it's going to be 2 over nl, and your Fn must equal n times F1. And everything we said before still, has that. So your fundamental mode is still called your first harmonic. second harmonic, third harmonic, fourth harmonic, and so on. And we still have your first overtone, second overtone, third overtone, n minus 1th overtone. And basically, you know, you can either think of it as like 1, 2, 3, 4, or, you know, original, and then the first after original, second after original, third after original, basically. And so you can probably see that for the pipes to resonate, you know, if we, instead of writing in terms of lambda 1, let's solve for L. So you can see that from this relationship, L must equal lambda 1 over 2. This L must equal lambda 2. This L must equal 3 lambda 3 over 2. And so you can probably see quite clearly that this L, oh, that's meant to be a lambda. So you can quite clearly see this L must equal n lambda n over 2. So for standing waves in an open pipe, what you need is the length of the string to equal n times lambda n over 2. As we said before, it's not just any string length and any wavelength. So for resonance of a standing wave in an open pipe, which basically is mathematically the same as a string, the condition is that L must equal n lambda n over 2. Now I want you to consider, is this the same for a closed pipe?